from PyLadies Malaysia, and I'm here to be your moderator. For our next talk, have you ever looked at a simple line of Python code and wondered about the incredible journey your data takes inside the computer? Where does it live? How does it get processed so quickly? Our next speaker is here to demystify all of that for us in the most creative way. She's a software engineer and an artist who uses delightful comics and the analogy of tiny Lilliputians to explain the hidden world of CPU caches, RAM, and storage. Please welcome Ava Katushka.
Hi, welcome to my talk. What do you need to know about computer memory as explained by Lilliputians, little people, computer memory in comics? And my name is Ava Katushka, and I'm a software engineer working at Bloomberg, and I'm also an artist. I'm really passionate about combining these two topics with explaining some extremely technical topics with art, make it more accessible. Somebody would say more childlike, but you know, I think we are all children, and I really enjoy books which are called Explain Me System Design, like I'm 10-year-old, like I'm 5-year-old, give it to me. I'm 5-year-old, I'm 30, but that's okay with me. So today, through art, through engagements and funny comics, we will explore all the levels of computer memory. We will start with CPU, then dive deeper into caching, then go and discuss RAM, random access memory, biggest working memory of a computer. And finally, we will discuss persistent and permanent storage solutions. So, couldn't wait to get started. Before we get started, I want to mention Ada Lovelace. Ada Lovelace is a first software engineer ever. Careful, she is not first woman software engineer, she is first software engineer, period. And I think it's pretty amazing. She was Regency era / Victorian era lady, and she was coding, she was writing algorithms for the first mechanical computer, which unfortunately was never built, but her ideas of what computers and computational would become are living a long living. She predicted a lot of things that we are currently experiencing with computers, and she was amazing. And we have like this connection. We are here, PyLadies, and she was a lady and she was coding. So if anybody would tell you you're code like a lady, you can be proud. It's Ada Lovelace, maybe, what they're referring to. Yeah, let's look at this small snippet of Python code. We have a list comprehension here, and we are creating a new array from the existing array by modifying each element of the array by incrementing it by 1. That is very simple line of code, but a lot of things are happening where we are making some arithmetical operations here. We are allocating memory. Where does this memory come from, what we are allocating? Really, where it's come from? Are there any limits that we could hit? We are copying the array. Maybe there is some limit on the size of array we could really operate in. Could you answer these questions right now? If not, I hope you would be able to answer that at the end of this talk, because we're gonna dive deep into them. And we're gonna dive deep into them by starting talking about registers. Registers are the smallest chunks of memory that our CPU has access to. They're like really, really small. The biggest of them is 64 bits, which is just like not a very big number. But what happens in CPU, all the action is happening where, as it does say here, action happens here. We are like multiplying numbers, adding numbers, incrementing numbers, doing logical operations with numbers. So these numbers are directly passed to the CPU while we do simple operations on them. And register space is pretty limited, but our CPU is capable of quite a big amount of operations per second. It's something around 10 to the power of 9 operations. That's why the frequency of CPU is measured in gigahertz, 10 to the power of 9. And this is not like the exact number of like all operations you come to the code, but it is good. Like rule of the thumb number for back of envelope calculations. And it's really useful to try to use it when we want to estimate how long something will take us, and or how bad or how good the algorithm is. Here I will introduce you some example. Imagine you have an array of 10 million numbers. That's a pretty big array, right? And you developed a quadratic algorithm to deal with that. How long would it run? Like, is it a good algorithm? Is it bad? We could estimate. So we get a 10 to the power of 7, put it in quadrats, 10 to the power of 7 multiplied 10 to the power of 7, 10 to the power of 14. This is how many operations we need to get to finish our algorithm. And when we divide it by operations per second our CPU is capable of, which is 10 to the power of 9, we get 10 to the power of 5 seconds. 10 to the power of 5 seconds, as it comes, is 27 hours. That's long, right? That's very long. No, we probably would not be able to wait till it completes. We would need to do something faster, right? On the flip side, if you had a linear algorithm here, it would finish well under a second, right? Or if you just had slightly smaller amount of input, instead of 10 million, we have 1 million, and we passed it to the same quadratic algorithm. We get 10 to the power of 12 here, 10 to the power of 12 operation divided to 10 to the power of 9, 10 to the power of 3 seconds. This is 16 minutes, and it's probably faster than that, like, because it's slightly more than 10 to the power of 9 operation. This is something we could live in. This is something you could wait for if you really wanted to. So this is the power that is given to you. By knowing this number, you are able to estimate operations in your system. Let's go deeper into CPU cache. Our CPU has a helper and it's a cache, and we have multiple cache levels. There is level 1 cache, level 2 cache, and level 3 cache, which is not featured on this image, but it could exist too. And what cache tries to do is try to predict what the next piece of memory the CPU will need. And you can see Lilliputians here like really excited. They're like, I could be called at any moment by the CPU. And there is an assumption which goes into the CPU structure, as we would think that data which stored close together is likely to use 2. So if CPU needs like one of the cells in which are stored close together, it's very likely it would need the other one too. Anything what really would fit in a cache line would be grabbed from random access memory to CPU. We will get into random access memory in just a minute. So the locality of how data is stored is really influential, and we will see it in example. So we want to implement stack. Stack is the simple algorithm structure. If you imagine a stack of plates stacked on top of each other, it's last in, first out. You can put the plate on the top, you can remove the plate on the top, And there is a few ways how you could implement it using more simple data structures. So one is popular way to implement it using linked list, and our popular way of implementing is using the array. What we know about array in memory is it's guaranteed the memory is stored close together, right? Versus linked list that each piece is stored in one chunk of memory, and when the other one could be stored in completely different chunk of memory, and they have a pointer to each other. From computer science point of view, both of these implementation would be equal. Linked list implementation for pop or push operations is of one constant, and so is array. Even array is slightly worse because of one in array is amortized. It means it's constant on average, and sometimes it's linear. But given what we know now about computer memory, which one really would perform faster? I will give you a moment to think about it. Okay, I hoped you had thought about it a little bit, and you know which one it is. So because of caching and locality of array, how all the elements are really stored together and really accessed faster. Access to CPU cache happens in tens of nanoseconds, 2 nanoseconds, 10 nanoseconds. The algorithm which uses array would be much faster versus linked list, because for each new element on linked list, we might need not only look into cache, but look one step further into random access memory to get it. And random access memory has maybe 100 nanoseconds to access it. So because of this locality of data, array has a huge advantage. Let's look into random access memory, which we already mentioned a couple times before. This is the place where your program runs. So Python program which you write here, like you written some Python program, it would load up and it would have its own space within random access memory. It could usually be maybe 1 gigabyte, 2 gigabytes. It depends on your setting on the environment that you have. And memory in random access memory is located sequentially, and piece of memory which you get is sequential. As we discussed before, sequentiality of memory does bear importance, right? It's working memory of a computer, so anytime, like when you close, if you restart your computer or you shut it down, everything in random access memory is cleared up, and on start again, it's get filled again. That's why it's often help to reload your system if something goes wrong. Yeah, it's like to joke about programmers, like the car is not working. Get out of the car and get back in again. That's what happens with random access memory. And access to random access memory is 10 times slower than access to cache. That you need to bear in mind. Finally, we get to our final and persistent and permanent storage, which we could really not live with. If we did not have a persistent storage, anything that we created would erase very quickly. So we really, really need it, which is stuff like your code, your photos, anything really that you want to be stored forever is stored in persistent storage, SSD, solid disk drive, or HDD. But you have to pay a price for accessing this permanent storage. It's about 15,000 nanoseconds to access SSD, which is 150 times slower than accessing RAM, and even 1,000 times slower to access HDD. So slow. Why do we even need HDD, you will ask? The answer is it's really budget friendly. HDD is cheap, is much cheaper than SDD. It's really great for backup. That's what happens in our persistent memory storage. Also, if you're one of those people who opens too many tabs, persistent memory storage really tries to help you out. So instead of storing all your browser tabs, all your running applications in random access memory, it would go and try to swap it up and store some of that on persistent memory storage, something that you're not using right now. But simultaneously, your experience become much slower. That's the price you have to pay. So to sum it up, we talked about CPU and operation happening in the registers, which really anything that you're running is ultimately happening. We talked about cache and how sequentiality of memory is important. We learned where your memory for your program is actually located in random access memory. And we learned all of these numbers of access which every programmer should know. How much time it takes to access some information from cache, from RAM, from HDD, from SDD. Now you know all of this and magic number 10 to the power of 9, so you can do your back of envelope estimation of how much time the system would really need. I hope it would help you, and I will end by mentioning another lady, Grace Hopper. She was the one who was writing the first compiler. She was a huge advocate for languages being more English-like and more readable instead of machine-readable. And if she, I think, coding with us right now, she would really be a PyLady, because Python is most readable programming language, I think, by my opinion. And yeah, she's really brave. She gave us great advice. Thank you for listening to my talk, and if you're interested in my art or in my thoughts, or you want to chat and contact me, this is my LinkedIn contacts. I would be so glad.
Thank you, Ava, for that wonderfully intuitive and artistic journey through the memory hierarchy. You have given us not just the what, but the so what, showing us how understanding these concepts help us write faster, more efficient code. It's a powerful reminder that behind every line of code, there's a bustling city of tiny workers we can learn to collaborate with. Let's give Ava another round of applause.